So we're very happy to have a talk by Ciprian Manolescu. Uh, Now, I almost said this evening, but I realize it's not this evening for many people. So we're very happy to have this talk as the first talk in the third part of the third day. And he will be telling us about generalizations of Rasmussen's invariant. So I'll let you take it away.
Okay, thank you very much for the invitation. It's a pleasure to speak here. I will be talking about several generalizations of Rasmussen's invariant to knots in three manifolds different from S3. And it's a survey talk, so some of it will be work that I did in collaboration with other people, and some of it will be just work of other people. Okay, so let's get started. Let's first review the usual Hovanov homology and Rasmussen invariant in S3. So I assume this is something many of you know. Hovanov defined his homology theory for knots in S3. It's a bigraded vector or bigraded abelian group. And the definition is quite simple. You look at the link diagram, you take all possible resolutions, and you get some circles. For every circle, you associate a two-dimensional vector space, V, and then you tensor them together. You add some shifts in grading, and then you have some differential, which is given by an explicit formula by multiplication and co-multiplication on V. And then you take the homology, and that's the definition of Hovanov homology. Well, with some signs, you have to add some signs. Okay, so that's a knot invariant that has been very popular in the last 2 decades. It refines the Jones polynomial in the sense that the Euler characteristic taken with respect to one of the gradings gives you the Jones polynomial when you keep track of the other grading as a power of Q. And it has something to do with 4-dimensional topology in the sense that if you have a link cobordism from in the cylinder in S3 times 0,1 between 2 knots or 2 links, then you get a map on Hovanov homology, and they compose nicely. So this is some functor from cobordisms of knots to abelian groups. It's what we call a topological quantum field theory. But a priori, this is limited to surfaces in S3 times 0,1. So we will see how to get to surfaces in other 4 manifolds. Okay, and there is a deformation of this story due to Eun-Soon Lee. So she constructed a spectral sequence. She changed the definition of the differential a little bit, and this gave a spectral sequence from Hovanov homology to a simpler homology, whose rank is just determined by the number of components of the link. It's 2 to the L. And in fact, you can specify what the generators are. There's one generator for every orientation of the link. And Rasmussen extracted from the spectral sequence basically by looking at the gradings of the generator some number called S. It's the average of the Jones gradings of the generators corresponding to an orientation and the opposite orientation with this formula. So it does depend on the orientation of the link. Okay, and then everything is still functorial with respect to link cobordisms. You can get a map of spectral sequences, and from this you can say something about the genus of link cobordisms in S3 times an interval. So here are some, okay, yes. So in particular, you get a lower bound for the slice genus. So that's the simplest 4-dimensional question we can ask about a knot. What is the minimal genus of a surface that's oriented, lives in 4 dimensions, in the 4-dimensional ball, and its boundary is the knot? Okay, so this is called the slice genus, and S over 2, using these functorial properties of Hovanov homology, you can say that this is a lower bound on the slice genus. In particular, this gives some obstructions for knots to be slice. Here's an example of a slice knot, a ribbon knot. If it bounds this disk, you can look at the color as being the 4th dimension, and you get an embedded disk in 4 dimensions. So this is a slice knot. And slice knots have GS equals 0, and therefore they need to have S equals 0. So if you find a knot for which S is not 0, then you know it's not slice. So this is an important problem. There's no known general algorithm for determining the slice genus or whether or not a given knot is slice. So we don't even know if this problem is decidable. But yeah, but we get some information from S. Okay, so here are some applications of this idea. So Rasmussen gave the first topological applications of Hovanov homology. He reproved the Milnor conjecture, which was originally due to Kronheimer and Mrówka, that, saying what the slice genus of torus knots is. It's given by this formula. Yes, and then you can also use S to show the existence of topologically sliced knots that are not sliced in the smooth sense. You just exhibit a topologically sliced knot. Alexander polynomial 1 implies by Friedman that it's topologically sliced, but then if S is non-zero, then you know it's not sliced in the smooth sense. And topologists knew that once you have such a knot, then you can show the existence of smooth structure, exotic smooth structures on R4. Okay, so this was the first hint that Hovanov homology can say something about 4 dimensions. Yes, and then there were other applications. I mean, I'm not mentioning all of them, but for example, Plamenevskaya had some applications to contact geometry, could do self-linking of transverse links. Piccirillo found knots whose shake genus is different from the slice genus, and then also showed that the Conway knot is not slice. Okay, great. Now, we want to see if we can go beyond that. So how about invariants of knots in other 3 manifolds? So first of all, you want to extend Hovanov homology, and this was done by various people. The first extension is by Asaeda, Brzezicki, and Sikora in 2004. They gave a definition of Hovanov homology for links in interval bundles over surfaces. So what's good about an interval bundle over surface? If you have a link in there, you can just project it to the surface. And then you have undercrossings and overcrossings, and you can get a diagram on the surface, and you can get a cube of resolutions, and you can kind of imitate the original definition. Yes, so that's something. The versions that were most popular were S1 times D2. So this is this is an interval bundle over the annulus, if you write D2 as I times I. And you can look at intervals, links inside here. Another name for this is the solid torus. And this is called annular Hovanov homology. And another popular 3-manifold of this type is RP3, the real projective space. If you take out a point, and the point doesn't matter that much, this is a twisted I bundle over RP2. So you can project to RP2 and again give a definition. The original one was with Zima2 coefficients. Later, let me skip to number 4, Manturov and Gabrovshek did it with Z coefficients for links in RP3. Okay, in a different direction, you can look at S1 times S2. This was done by Rozansky. It's a little bit more complicated. We'll get to it in a few slides. And then Willis extended it to links in connected sums of S1 times S2. And more recently, well, 6 years ago, Morrison, Walker, and Vedrich did it for links in any 3-manifold, but in a completely different way, so a less algorithmically computable way, let me put it like this. They defined something called the Skane lasagna module. So this depends on a 4-manifold whose boundary is the 3-manifold, and you put the link in the boundary. In particular, when you have B4 with boundary S3, then you get the original Hovanov homology. Okay, so these are some of the extensions. And I will discuss the corresponding generalizations of S. So this is what this talk is about. Yes, there are many generalizations of S just for knots in S3. You can use SLN homology. You can use Stirrad squares. You can use many other things, but I will focus on just extending the original S, but to links in other three manifolds. And also what they can tell us about surfaces in other four manifolds. So far, we just had surfaces in S3 times an interval or in B4, which is closely related. Okay, so let me start with the annular Hovanov homology. So there we have diagrams inside the annulus, and you can redefine Hovanov homology. You take resolutions, and the only thing that's interesting is that there is a third grading because some of the resolutions go around the whole, and you associate a different graded vector space to that. Okay, great. And then you can deform it. You can do a Lie deformation. This was done by Grigsby, Licata, and Verley in 2016. And because you have three gradings, you don't just get one Rasmussen invariant, you get three of them. You get infinitely many of them, but they depend on a parameter. So in 0, 2. And all of them give you bounds on the genus of knot cobordisms in I times the solid torus. So now we're talking about knots or links in the solid torus. And we're talking about cobordisms in an interval times the solid torus. Just like before, we had an intervals times S3. That's good. They also have some applications to properties of braids, because if you have a braid, you can close it up inside the solid torus, and this tells you something about the braids, some properties, if it's quasi-positive or right veering, and they give some constraints on that. I will not get into the details, but that's what they did. Okay, so now let's move on to S1 times S2. So again, the Hovanov homology was defined by Rosansky and then extended to connected sums of such things by Willis. For the purposes of defining the Rasmussen invariant, we're going to assume that the link is null homologous in S1 times S2. It gives the zero class. Otherwise, things don't work as well with respect to the gradings. Okay, so how do we define these things? Well, first of all, how do we draw links in S1 times S2 or a connect sum of S1 times S2? We choose some pairs of balls inside S3, and then we think of this as a handle. Basically, we drill out the balls and then we identify their boundaries. This gives us an S1 times S2, and this gives us another S1 times S2. And this is a picture of a link. It just comes into one handle and comes out the other handle. Okay, so now what else? We can get a link in S3 from this by inserting full twists. So this box with K1 means K1 full twists. And you insert many full twists like this. You get some diagrams, dk. K is how many full twists you insert. And then you take the limit as you insert more and more full twists. So of course, this is infinite dimensional, but you do some grading shifts, and then it turns out that after you shift the grading, then it stabilizes in each grading. And that was...
Excuse me, just to clarify, the twists are in the handle direction? They're along the handles?
Yes.
Thank you.
Yes, right here. Yes. Okay, great. So you get some diagram, and this is how you define Hovanov homology. Okay, so now what did we do? So with Marengon, Charcot, and Willis in 2019, we defined a Lie deformation of this theory, and we defined an invariant S, similarly to what Rasmussen did for null homologous knots or links in connected sums of S1 times S2. And from here, of course, we get bounds on the genus of link cobordisms in an interval times this manifold. More interestingly, okay, we get bounds in some other four manifolds. Well, what are some four manifolds with this boundary? For S3, it's clear what's the simplest four manifold is with that boundary. It's B4. For S1 times S2, we have two choices. We can either think about B2 times S2 or S1 times B3. And okay, and if you have connected sums, you take the boundary connected sums of these things, and you can define, instead of the slice genus, you can define a slice genus in each of these manifolds, and you get lower bounds for both of them. They're slightly different. So in one of them, you get S over 2, and in the other one, you get minus S of the mirror divided by 2. These are two quantities that turned out to be the same in S3 for ordinary S, but for our S, they're not the same in general in S1 times S2, for knots in S1 times S2, so they give you different bounds. Okay, so that was something. More interestingly, somehow you can use this S to also tell you to also get something new about the S invariant of ordinary knots in S3. So, right, so the reason for this is that these diagrams basically from every knot in S1 times S3, every link in S1 times S2, you get a family of links in S3. They also depend on the diagram and then on how many crossings you do. But it stabilizes, and we can show that also the S invariant stabilizes, and we can say exactly when it stabilizes. So S of k, this is the S in S1 times S2, and this is the ordinary S in S3. They're the same when you twist at least that many times, where this is the number of positive crossings. Okay, in particular, when you have 0 positive crossings, then you just need to twist once, because this is 1. Okay, so this gives you, it gives you the S invariant of this interesting link. You'll see why it's important. This is a null homologous link in S1 times, let me start with the one in S1 times S2. This one has no crossings. It just consists of like 2p fibers in S1 times S2. S1 times something, it has 0 crossings. And if you twist it once, you get a torus link. Yes, and you have to orient it like in pairs. So the same number of strands go up as they go down. This makes it null homologous. And well, there are some methods for computing the S invariant in S1 times S2 with Hochschild homology. And from that, we can get the S invariant here. We get it to be 1 minus 2p. Okay, so you can compute some new S invariants. The reason why this is interesting is that it tells you something about surfaces in CP2, in the complex projective space, minus a ball. So the bar means that we reverse the orientation. This is just a convention. You can do it the other way. And you get a bound with minus S of minus K. Okay, but let's focus on this. So we have the connected sum of as many as you want CP2 bars. This is a 4 manifold. You take out a ball, you get boundary S3. You can look at the knot in here, and you can ask about the surfaces with boundary this knot. Okay, so just before we were looking at surfaces in B4. Now we're looking at surfaces in a more complicated 4 manifold. Okay, and the claim is that S over 2 still gives a bound on the genus of a surface in here, assuming the surface is null homologous. Okay, so why is that true? Well, we can look at this surface and see how it intersects the core of CP2 bar, namely CP1, which is a sphere. And if it intersects it in 2p points, what happens is you look at the neighborhood of it, and you get a cobordism in the ordinary cylinder in S3 times 0, 1. and it goes from the knot K to a fixed link. In fact, it's like 2p copies of the hop vibration, which exactly is the link that I showed you on the previous slide. So from a cobordism in CP2 bar, you get an ordinary cobordisms in the cylinder, and you get some inequalities between the S invariant here and the S invariant of this link. And since we computed the S invariant of this link, then this gives us this genus bound. Okay, so this was an application to surfaces in other four manifolds. Okay, so I should say since then, a couple years ago, Rern gave a more elementary proof of this formula using just traditional Hovanov homology, and he also computed basically S of all torus links. And using that, he generalized our adjunction inequality for surfaces that are not null homologous. So if they have any homology class, you get this kind of bound involving the Euler characteristic of sigma, the homology class squared, and this is basically the norm of this class. Like this lives in Z to the R, and you just sum the absolute values. Right, so this is a general inequality for such surfaces. It's similar to what was proved in Hegardt-Flood homology for another invariant called the tau invariant. And, you know, people thought that maybe you need something about gauge theory or functoriality in other four manifolds to prove such a thing, but somehow you can prove it for the ordinary S invariant using this kind of tricks. Okay. Next, all right, so this was S1 times S2. Next, I want to talk about RP3. How do we draw things in RP3? So I said before, we project them to RP2. And we present them by projections. Okay, I should first say there's two kinds of links, class 0 and class 1, according to their homology class, which is ZMA2. In particular, there's the simplest knot in each of these classes. There's the local on knot in R3 and RP3 in the 0 class, and then there's RP1, which I'm going to call it the class 1 on knot in RP3. Okay, but if you have a general knot in RP3, you present it like this. This is a diagram. In RP2, the antipodal points are identified. So maybe, I don't know, I start from here, I go over here. It's identified with this. I go like this. I come out on this side. Boom, I come out. Where do I come out? I come out here, then here, and then I come back where I started. So this is a knot. Okay, and if you have a diagram like this, you can do a cube of resolutions, and you can define something like basically a generalization of Hovanov homology. This was done, as I mentioned before, by Asaed, Sikora, and then Manturov and Gabrovshek, they did the signs. In joint work with Willis, a couple years ago, we constructed the Lie deformation, and we defined the Rasmussen invariant. And as usual, so this is for links in RP3, and we get genus bounds for cobordisms in the interval times this 3 manifold. Okay, so we can also define some sort of slice genus. The slice genus, the ordinary one, is the minimal genus of a cobordism between a knot and the unknot. Here, for a class alpha knot, we define it to be the minimal genus of a cobordism between your knot and the class alpha unknot, either the ordinary unknot or RP1. Maybe I should say you can only have cobordisms between knots of the same genus, of the same class. Okay, so what we proved is that, again, in this context, we get a lower bound on the slice genus of the knot. S over 2 gives you a lower bound. All right, so we get something like this in RP3. Here is an application, a concrete application. So if you think about cobordisms in an interval times RP3, the simplest thing you can ask is whether there is an annulus. So if so, you say that they're concordant. Just like in S3, you said that two knots are concordant if they co-bound an annulus in I times S3. So we have an example that there exist knots that are not concordant in RP3, but when you lift them to S3, they become concordant. So the lifts are concordant. Right, yes. And for this, well, how do we do it? Well, here are some knots. Basically, we need to find a knot such that S of K tilde is not 2 of S of K. For many knots, if you look at S of S in RP3, then S of the lift is twice as much. Like we see this for a lot of small knots, but then by computer calculations, we found some knot with 6 crossings in, actually, I think it's the knot I just showed you. Yes, this one. It has 6 crossings in RP2, and then when you lift it to S3, it becomes 12 crossings, and this is the lift. And we computed, and they're not the same. And once you have that, basically there's some easy construction. You look at K and then minus K plus K tilde, where K tilde is the lift. These are 2 knots in RP3, and you can check that basically they have different S invariants, so they're not concordant, but when you lift them, they become concordant. Okay, so in other words, you can think about their lifts. Their lifts are what are called freely periodic knots in S3, in the sense that they're invariant under this involution. That's the free involution on S3. And they are concordant there, but they're not equivariantly concordant. You cannot have the concordance preserve this symmetry. Okay, now what else can we say from RP3? So before, for every 3 manifold that we discussed so far, we had like a simplest 4 manifold with dot boundary, well, or several. But in the case of RP3, there's also a clear case of what should be the simplest 4 manifold with boundary at RP3. It's the disk bundle for the tangent bundle to S2. Let's call it DTS2. Okay, so this has boundary RP3. And Run proved that we have a genus bound for surfaces in this bundle, right? So far we just had, you can always do your 3 manifold times an interval, okay? But that's, that has a different boundary, so we don't like it that much. But here is a 4 manifold with a single boundary, which is RP3. And you can show that if you have a surface in there, then you need some condition on the homology class that its absolute value it's at most 3, but then you get this lower bound. G over 2 is bounded below by minus S minus D squared over 2. And again, the idea is that it's similar to what we did in CP2. You look at how this surface intersects the core of your 3 manifold. In this case, it's just S2. You think of this as a disk bundle, and you look at the 0 section, and you get some cobordism in I times RP3 to a fixed link. And if you can compute S of that link, you get some bound for the knot itself. Okay, now here's another extension in RP3. So we had one, but there is another one. So this was done by my student Darren Chen. He studied a different deformation, similar to the one done by Barnard in S3 with Zima2 coefficients. And you get a slightly different invariant, SBN. And what he showed is that this gives lower bounds. So you get some bound on the Euler characteristic of a surface in RP3 times I. But instead of orientable surfaces, by the way, all the surfaces I discussed so far were orientable. This version of S gives you bound on the twisted orientable surfaces, meaning that the ones that have an orientation that is reversed, such that the lift to S3 has an orientation that's reversed under the deck transformation. So if the surface was orientable, then its lift to S3 times I would be orientable there, and the orientation would be preserved under deck transformation. If it's reversed, then it's called twisted orientable. And there are well, there are orientable surfaces that are twisted orientable, and there are twisted orientable that are not. Any of the four possibilities, it happens. It can happen. They're independent concepts. Yeah, so here's a concrete application. Here's a knot in RP3 that bounds an orientable slice surface of genus 1, but it doesn't bound a twisted orientable and orientable surface of that genus. Okay, so we can say something also about this kind of surfaces. All right. Okay, so we did annulus, we did S1 times S2 and its connected sums. We did RP3. Now let's go to the general case. So there is something in the general case, although it's quite different. It's not as computable. The Skane lasagna module. This was defined by Morrison, Walker, and Vedrich. And let me go over the definition. So we have a link in a 3-manifold, and the 3-manifold is the boundary of a 4-manifold. We have to specify which 4-manifold we want. Okay, so then we talk about these lasagna fillings, which are as follows. You have some balls inside the 4-manifold. You have some links on the boundary of the balls. And you have some cobordisms from your link on Y to these other links. They might have components that are like this or even closed, okay? But just some cobordism. And then we have some labels. So for each of these other links, they live in S3. So we have their Hovanov homology is well defined, and we label them by that. Okay, so that's a filling. Okay, and we're trying to define something like the Hovanov homology of this link, but this lives in a different 3-manifold. All right, so what can we do? We take a linear combination of all the fillings with that boundary, and we divide by some equivalence relation as follows. Well, we make everything to be multilinear in these VIs, but more importantly, we allow for, if we fill in a ball, we set these two things to be the same. So what does it mean to fill in a ball? It means that you replace this filling by a bigger filling to maybe some smaller balls, but you impose a relation. So if you have these labels here, you want the ordinary Hovanov map in this cobordism to take these labels to the original label. Okay, so that uses maps on Hovanov homology in the complement of some balls inside another ball. That's not too bad, right? If you have a single ball, then that's just S3 times I, and we know cobordism maps there, and they generalized it to this situation. It can be done in an elementary way. But basically what you do, you can think of this as some sort of Skane module, but at the level of homology groups. So you look at all possible fillings, and then you divide out by all the local Skane, all the local relations. Instead of Skane relations, you have cobordism relations on Hovanov homology. Okay, and you divide and you get this. A priori, this may not be finite dimensional. In fact, it's not for sometimes, but it is in many cases. And it's also not clear how to compute it, right? Because you have all the possible fillings, all the possible balls inside your 4-manifold. Okay, nevertheless, you can compute it in some cases. So let me make some remarks. You can, well, first of all, it decomposes according to the relative homology classes of the fillings. When you have before, you get the ordinary Hovanov homology for your link. And then some non-trivial calculations were done in my paper with my student Nate Halat from 2020. We looked at a case when you attach two handles to B4 along another link, K. So, for example, CP2 minus a ball is obtained like this by attaching a handle along an unknot. So now you have the original link inside the boundary of this manifold. Then you have the link along which you attach the handles. You have K and L. And what we showed is that in that case, you can compute the Skene lasagna as a direct limit of Hovanov homologies of the union of your link and cables of K. And you have to consider infinitely many cables. Okay, so this is a formula. It involves infinitely many terms. And to apply it, you need to understand some Hovanov homology of cables, which is not always easy, but again, in some cases, it can be done. Okay, so this was for two handles. Now, in general, a four-dimensional manifold can be split into handles of different degrees. So one handles, two handles, three handles, maybe four handles, and zero handles. And two handles are the most complicated in a sense. But so starting from this, in joint work with Walker and Vedrich, we gave a general description, like a general kind of formula in terms of handle decomposition for the Skene lasagna. Again, it's a formula that involves infinitely many terms and some limit, but it's more concrete than just all possible fillings modulo that equivalence relation. It's in terms of the ordinary Hovanov homology. Okay, so starting from that, we did some computations. I guess in our paper, we looked at CP2 and some disk bundle over at S2. And then Sullivan, Zhang, and Run and Willis, they did more computations. They computed S2 times S2 in general. They got 0. And then, for CP2, you get 0. For CP2 with the opposite orientation, you get something non-trivial. So you can compute it for some simple four manifolds. Oh yeah, for now, we can actually look. So this is interesting even when the link is empty. But the four manifold can be anything with boundary. Or it can be closed. Okay. All right. So, okay. So since we want to talk about the Rasmussen invariant, the extension again was done. 1 year later, independently by Morrison, Walker, Vedrich, and Run and Willis, they did the lee deformation. Run and Willis did a little bit more. They identified the generators, and they defined this S invariant. I mean, Morrison, Walker, and Vedrich also defined an S invariant, but slightly different. So anyway, it's some S invariant that, in the case of B4, recovers the original one. And now it satisfies a genus bound in an arbitrary four manifold with boundary. So if you have any four manifold with boundary L, then you get this inequality that involves the S invariant of X and L and the homology class. It depends on all that, but it tells you a lower bound for the genus of such a surface. Okay, so this sounds great, and it is great, but still there are some issues. So one thing to keep in mind is that in general, there's no algorithm for computing it. Whereas for the concrete cases we had before, like, you know, S3 and RP3 and things like that, you can compute it, you can plug it into a computer. Here, it kind of does an infinite limit definition, so it's more complicated to compute. You can still do it in some cases. And also it can be minus infinity, like for S2 times S2 or for things like that. And if it's minus infinity, then this genus bound is vacuous. You don't get anything. All right. Nevertheless, it had a really striking application. I mean, I know Run gave a talk yesterday, but I'll just review it. So using the formula for the two handle bodies, you can look at some simple two handle bodies, namely surgeries on a single knot. So you just attach a handle along this knot. You attach a disc with this boundary on the ball. You attach it to B4, and then you smooth the corners, and you get a four manifold with some boundary. They looked at these two knots that happen. Well, so when you do this attaching of the handle, the four manifolds are different, but the three manifolds that are the boundary are the same, it turns out. So one knot is 5,2 and the other is this pretzel knot. Okay, and you just consider the empty link on the boundary, but then you get an S invariant. You get an S invariant for the four manifold, and you can compute it, and you get different answers. So in one case you get 3, and in the other case you get 1. maybe I should say how you compute it. So you use some properties of these things. You use that one of them is positive and the other one is slice. And you use something we know about Hovanov homology of cables of such things. And the formula I proved with Nate a lot for two handle bodies involved cables of these kind of knots. I mean, you don't have to understand the Hovanov homology precisely. You just have to get some bounds on the S invariants from that. And you can do it for both positive knots and slice knots. Okay, so since the S invariants are different, you get that they are not, the four manifolds are not diffeomorphic. However, it follows from the work of Friedman that they are homeomorphic. So this gives you a proof that they are an exotic pair, homeomorphic but not diffeomorphic. This was known before. It was due to Agbolut, but Run and Willis gave the first analysis-free proof, so without gauge theory. And they also have some new exotic examples, also from some knots that are detectable using this lasagna S, but not immediately using gauge theory or Hegar-Fleur homology. I mean, maybe they can be done like that, but the computations are harder in that setting, and they can be detected using S. So to this extent, Hovanov homology can be used as a replacement of gauge theory. I mean, we knew this already from Rasmussen because it was happening for, it was given the exotic R4, but now these are compact examples, which are typically harder. Right, so let me end with some open problems. Okay, so first of all, we have the Skane lasagna module in general for any three manifold, for links in any three manifold. You have to specify the four manifold. But we also have some more concrete things for things like S3, RP3, and S1 times S2. And those are easier to compute. And it would be great if we could extend Hovanov homology and Rasmussen invariant for links in other three manifolds in a more concrete way. And the first candidates to look at are the length spaces. So RP3 is L21. I think the next simplest thing would be L31. Probably if you can do L31, you can do LPQ for any P and Q, or at least LP1. And yeah, you can draw diagrams for such things, but it's not clear how to get an invariant. Okay, so that's an open problem. Another one, let's see. Yes, so there is this idea that you can maybe use the S invariant to find exotic four manifolds using the properties of this inequality about the genus bound. So in an open problem is whether there exists exotic CP2 bar or exotic CP2 or exotic connected sums of this. In particular, if you have R equals 0, that's an exotic S4. That's the smooth four-dimensional Poincare conjecture. So there is this hope that maybe if you could show that the S invariant, the inequality, we had an inequality for surfaces in this manifold. There are examples of potentially exotic CP2 or a potentially exotic S4. And if you could find a knot that bounds a surface, you just have to construct it, and it violates that inequality, the same inequality, then you would show that that manifold is exotic, right? But okay, so yeah, with Lisa Piccirillo, we tried this for some examples, but in the end, it didn't work. I mean, it could be that the S invariant satisfies the same inequality in the exotic CP2 bars as well, or in fact, it could be that such exotic things just don't exist, but that's still something worth trying. Okay, what else? In RP3, we had this example of knots that are not concordant, but when you lift them to S3, they become concordant. Interestingly, we don't have examples of knots that are not slice, but when you lift them, they become slice. So something that's concordant, that's not concordant to the unknot, but when you lift it, it becomes concordant to the unknot. So this is a concrete problem that in principle could be tractable using the S in RP3, but we just don't have the right example. And yeah, I don't know. That's something that one could try to do. And finally, for the skein lasagna, okay, so Wren and Willis detected exotic smooth structures on some compact four manifolds. Those have boundary. So an interesting question is whether you can do that for closed four manifolds. Again, the skein lasagna is well defined, and the only challenge is to compute it for some non-trivial examples on closed four manifolds. All right, so I will stop here. Thank you.
Thank you very much. That was great. Thank you. I'm going to turn off recording.